All right. Good morning, everyone. Morning, and welcome to this session on how code rots at machine speed. So the big question we're going to take on today is that we all know that an AI can write code. The big question is, can it write good code? And even more important, can it maintain its own code? And I promise you that we're going to cover both the good, the bad, as well as the slightly ugly side of AI. But let's start by taking a step back and see where we are and where we are heading. So Markus, please.
Thank you very much. So great to see so many people in the room. I'm an academic researcher, so I like to start with a paper. And I want to start with this one, published in 2012, on the naturalness of software. So this was published in the prelude of using deep learning for natural language processing. So this was before Google Translate and the other translators went all in on neural networks. And at this point in time, Hindle here in the picture and his colleagues published this paper where they showed that programming languages are more repetitive than natural languages. And a quote from the paper is the following: "Programs that real people actually write are mostly simple and rather repetitive, thus they have usefully predictable statistical properties." And this is really the foundation. This is why large language models work for code. And we're in 2025 now, and we've seen this widespread adoption of AI tools, right? These are figures from this year's Stack Overflow Developer Survey. 84% of the respondents this year claim to be using AI tools. So a lot has happened since the first wave of AI tools hit us in industry. So in 2022, Copilot came with its code completion, right? And then we had a second wave with chat-based programming, spearheaded by ChatGPT. And now we're in this third wave with the coding agents, such as Claude, right? And what we now expect to see more of is those multi-agent solutions where you combine different coding agents. It's a very interesting time to be an academic researcher and study this. A lot is happening. It's never been changing as fast as now. But if we take a step back and look at the big picture, what we clearly see is that humans are less and less involved in this future in writing the code, right? We leave it more and more for the machines. So, moving on. What's the biggest problem with code? Well, it has never been writing it. It's about having it, right? The more you have it, the bigger your problems tend to be. And I want to highlight this prominent research from Norway, Professor Dag Sjöberg here in the picture. Some 15 years ago, they used a lot of oil money in Norway to bring in consultants to the classrooms and do controlled experiments. And among other things, they looked at correlations between code smells in code and maintenance effort. And here is the really interesting takeaway from that series of studies they conducted. File size and the number of changes explained almost all of the model variation in effort. So this is important, because now we have this situation with AI tools changing things. We almost see that the cost of code creation is approaching zero, right? And I want to bring in a concept from sustainability studies, and actually we heard about it also in the brilliant keynote you just attended, Jevons paradox, or the rebound effect. So the Jevons paradox is the extreme of the rebound effect. So I'll stay with the rebound effect here. So it refers to the improved efficiency leading to more of some use, and then there will also be systemic responses that actually shrink some of the expected gains. And the textbook example of the rebound effect, this is what also is called the Jevons paradox. It's about burning coal. So steam engines during the Industrial Revolution became more efficient. They needed less coal, but then more factories found it very attractive to install those steam engines. And the total amount of coal burned here, for example, around the Manchester area, increased a lot. And there was heavy pollution as a consequence, right? But back to code, we have this increased efficiency now in creating the code. We will inevitably see more code being produced on this planet than we've ever seen before. We'll see changed code churn. And pretty much what you see here on the left-hand side, what challenges maintainability, we are really setting us up for a rebound effect here. But Adam, change is the only constant, right? Haven't we seen disruptive tech shifts before?
We definitely have. And I think this is one of the most common reactions or maybe questions I get, that isn't AI coding just like the move from 1970s assembly languages, machine instructions, to high-level languages? And I think that AI coding is not a natural progression in abstraction. AI is very different, so I think that comparison is flawed. And the way AI is different is because this is the first time, it's the first time ever that we adopt a non-deterministic technique for writing code at scale. So with non-deterministic coding, we have to adjust our ways of working accordingly. Because over the next few years, as Markus has pointed out, we will see more code than ever before, and it will be delivered at a faster pace than ever before. But that code is of a largely unknown quality. So I do think this is a fair question to ask. What could possibly go wrong? Right? Because you see, the acceleration we get from an AI just isn't useful if it's driving our project straight into a brick wall of technical debt. So we need to ask ourselves, what characteristics, what qualities, what guarantees do we need to set for our code now that its creation is more or less free? And a very quick spoiler, which perhaps isn't so surprising given our backgrounds, but code quality and maintainability have always been important. But they're even more so in the age of AI. And this might surprise some people. So has anyone seen this fantastic headlines before? Right? So there simply won't be any human programmers in 5 years' time, and this was said 2 years ago. Guess what that CEO is selling? An AI platform, who would have guessed that, right? So Markus, keep me honest, am I being too cynical here?
Well, we'll see what the future holds.
Yeah, definitely. So we can easily discard this as marketing hype, but what surprises me a bit is that even more tech-savvy CEOs, like for example Mark Zuckerberg, he made this claim that by 2025, all mid-level engineers will be replaced by AI. And to Zuck's credit, I mean, there's still 1 month left to go of 2025, so we never know. But all of this begs us to do a reality check, to take an honest look. Does an AI write good code? So I made an experiment here. I'm running Copilot in VS Code, and I'm running it on some real production code. So what you see here on screen, and again, the details aren't that important. I know that it might be a bit blurry on the big screen, but just look at the large picture here. So I have a piece of code here, and it's a piece of code that listens to keyboard events. And what I want to do now is I want to extend it with some new functionality for collecting usage statistics. And I want these usage statistics to be published in Amplitude. So if you haven't heard about Amplitude before, it's basically, think of it as a SaaS event store, right? So you publish events, you can then analyze them, do stats and whatnot. So I'm prompting Copilot, and I ask it to generate the code. And it's thinking for me, and it spits out a solution. Wonderful. The nice thing is, it's not that much code, so we can actually spend some time reviewing it and see, is the AI capable of writing good code? So by looking at this code, the first big problem I see are structural. So from a structural design perspective, this code is quite flawed. It lacks modularity. It does way too many things, making it hard to reason about, making it fragile to change. We also see this dreaded anti-pattern of deep nested complexity. Can you see that? That also worries me, right? Because again, it makes the code very hard to reason about. If we, instead of critiquing the design, looks at the reliability of this code, I think it's fair to say that the error handling is flawed at best. Because C++, which this code is a language with exceptions. And this code is exception ignorant. So the moment anything here goes wrong and an exception is thrown, we're going to leak resources all over the place, right? Probably not a prize-winning design. But to compensate for that, and maybe adding insult to injury, the AI was friendly enough to swallow all our exceptions for us. So where does that leave us? Well, if something goes wrong, things will go horribly wrong, And worse, you won't even know about it. And of course, I could move on and I could start to nitpick on stuff like, hey, you're using magic numbers. You have this null bomb that doesn't reveal anything whatsoever about the intent of the code. But I'm not going there. I'm going to let AI off the hook. But a better question here is maybe, by a show of hands, who would like to maintain code like this? Not so many people. It's really only me. Wow. So maybe instead ask, who would like to maintain hundreds of thousands of lines of code like that? Which is what's going to happen in a month when Zuck has replaced all of us. So I think we're in for interesting times. And as Markus pointed out, writing code is fast now, right? So generating this technical debt, which was like 20 lines of code, took roughly 30 seconds. So how much technical debt can we create in a day with AI acceleration? In a week, in a year? So it's very clear that we cannot blindly trust an AI to put complex code into production. So we humans need to be in the loop. And that means that human comprehension is going to be the bottleneck, right? And what happens when a human experts need to step in to fix AI-written code? What risks and what's the learning curve? And I do think this is part of a larger challenge, isn't it, Markus?
It is part of a larger challenge. We've heard about it in the keynote as well, right? We have to adapt. So how many of you have had a look at this year's DORA report, State of AI-Assisted Software Development? There are not too many. It's an interesting read, actually, recommended. If you just have a look at the executive summary there, you will see that they describe AI as an amplifier. An amplifier of things good and things bad alike, right? So we tend to agree with that, which means if you work in an organization with terrible technical debt management processes, the AI code will be yet another burden to tackle, right? And it's actually something that might spiral out of control and potentially also turn into an existential threat. If you look at the other side of this spectrum, the happy robot comes here and says, yeah, AI will be this game changer, right? For a well-functioning organization with practices and processes in place, it might very well, help you speed up, deliver high-quality features, and we will see. But as we heard from Simon in the keynote, we will all have to adapt, right? We live in this normally distributed world of organizations. Some organizations will adapt better, and they might outrun the ones in the middle, right? So we all have to think about this and think about it carefully. So what do we do with this information in the future, Adam?
I do think it's safe to say that we need to safeguard on AI in order to get the most out of it and to benefit from the acceleration. And that to me means metrics. We need to define some metrics that we can use to drive maintainable code, be it written by humans or AI, right?
Right, I happen to like this as well. So I'll give you a very brief introduction then to the scientific background of coding research. So in science, we like to study constructs, and a construct is a theoretical concept. It's typically something you cannot measure. And our favorite construct, you might have guessed already, it's maintainability. So it is a valid and well-defined construct. From ISO IEC 25010, for example, it's defined as the degree of effectiveness and efficiency, so both these qualities, with which a product or system can be modified. So this has been around for a long time. Now we want a metric, and this is a countable way to measure something. And what we learned from the Norwegian research, and other researchers have shown this as well, size is a very naive, but actually not too bad a metric when it comes to predicting maintainability effort. Humans do not like very big things, especially when they have to understand what's going on. But we do have something better, don't we, Adam?
We do. We have something that's quite different. Because many years ago, we set out on the challenge, can we define and measure high-quality code? And it turns out to be a really tricky challenge, because if I ask you what code quality is, you will probably give me multiple different answers, and they might even be in conflict with each other, right? And that's because code quality is a very vague, very subjective, and very multifaceted concept. So what we did was that we started from the other direction. We said that if it's hard to agree what good quality code is, maybe it's easy to define what bad quality is, right? that I think we can agree on. So what we did was that we defined a concept called code health, which is also the name of the metric. And the way it works is that we start from a file. We take a file with source code, parse it, and then we analyze that code for various code smells. And these code smells, they come in 3 different categories. So we start at the module level, look at the class design. And here we might look for things like low cohesion. That's very common. So who's familiar with low cohesion, the code smell? So it's like maybe 4 of you, 25%. So low cohesion is basically when you stuff too many business responsibilities into the same class, the same module. Now that code is hard to understand because you need to understand all these different business requirements, right, to make sense of the code. And of course, once you start to change it, it's very easy that you introduce some kind of unexpected feature interaction, and all bets are off. Then at the function level, we might look for other problems. A classic example here is copy-pasted code. Is that excess copy-paste, is that a good idea, Markus?
It's typically not a very good idea. No, it's a big problem, and we're going to see more of that, unfortunately, going forward.
Most likely. And we have also favorites, like my personal favorite, primitive obsession. Anyone heard about that? Yeah, some of you, cool. Primitive obsession is you have a public API, and it typically takes a lot of arguments, and all of them are primitive built-in types, which, first of all, makes it easy for mistakes, like just misplacing 2 arguments. And they don't constrain the range, and also they don't communicate anything about your domain particularly well. So very common code smell. And finally, at the implementation level, we look for accidental complexity in how the code is written. And we already saw one example in the AI-generated code with deep nested complexity, right? So anyway, we look for these code smells and a bunch of others. There are 25 in total. And then based on what we find, based on the frequency and the severity of the code smells, we weight them together and can now categorize and label every single piece of code as being in one of these 3 different categories. And where you want to be with your code and with AI code is you want it to be healthy, because healthy code is code that's easy for us to understand. It's the absence of these code smells. However, a metric on its own, it's really just a vanity measure. So we wanted to make sure that whatever we measure and use in our research as well, that it carries a meaning, to the business. So many years ago, we did something called the Code Red study to look at the business impact of code quality. So when was that, Markus?
That was published in 2022, so we did it the year before, I guess.
Yeah, so like 4 or 5 years ago. So it predates the whole AI movement, which is kind of interesting. So what we did was that we looked at these 3 different code health categories, and we looked at how do they correlate to development speed and defect reduction. And you see in the graph here, you see the development speed. So it turns out if you have green code and you want to make a change to it, add a new feature, you can typically be 10 times quicker than someone making a similar change to red code. So there's a very clear speed advantage to high quality code. And of course, there's also the risk for defects. If you have green code, you have on average 15 times fewer defects than anyone having red code. So there's a massive advantage to code quality. And perhaps even more important in this AI age, where we generate more code than ever before, that we as humans have to understand as well. Green code is twice as quick to onboard yourself in compared to problematic or unhealthy code. So there's a strong onboarding advantage here as well. And we have taken it further since the Code Red study all those years ago.
Yes, we keep studying our metric in various ways. One thing we have done is benchmarking studies. So benchmarking, I think that's an interesting concept. It never tells you the whole story. I mean, how fast a car accelerates, for example. I mean, it doesn't tell you everything about the car. But it tells you something that is relevant if it's a good benchmark. And the best available maintainability benchmark was established by the Technical University of Munich in Germany, where they carefully sampled 304 Java files, and then they brought in professional developers to annotate those in a smart way. And what we'll look at now is simple binary classification, so just taking a file and answering whether or not it's easy to maintain or not. And the results I'm going to show here have F-score on the y-axis, so this is a harmonic mean between precision and recall. A very important first mark in this bench is what the average human expert did here in this study they did in Germany. And 88% is the answer here. So this shows that maintainability is not a trivial problem, right? There's subjectivity to it, but by having a majority voting, they established this ground truth. And 88% is what the average human did. And then we have size. So the kind of Norwegian suggestion here, just counting lines of code. And it takes you far, actually, 78% here on this benchmark. Just pointing out which files are big. But there is a big drawback with this, and that's the fact that lines of code, it's not an actionable metric. What you get as a developer is simply that this file is big, you should probably split it. But what we want is a metric that actually gives you a recipe for how to improve things, right? Something that is code smell based, and there are a few. Of course, we had a look at code health. What it's delivered here, 83% was the result. So it's a little bit better than lines of code. That's good. And then we also checked some alternative metrics. You might have heard about the maintainability index. Was proposed in the 90s, so a while ago. Comes in at 59%. And we have the TD ratio as offered by SonyCube, and it performs very bad actually on this data set. It comes in at 12%, so there are so many false positives here. But we are pretty convinced now that code health, it aligns very well with human maintainability judgments, and this is something that's of course very useful going forward. But what's then the next question, Adam?
Yeah, I think the next question is that we've already seen how an AI can generate code that's suboptimal, right? That doesn't really align with the way we want code as humans. And that code suffers from low code health. But the question is, of course, what are consequences when that happens? So we know that we as humans will struggle with understanding poor code. But maybe we don't even need to understand it going further, because maybe the AI is smart enough to understand it. So maybe an AI can get us out of that deep pit of accidental complexity. So the big question here is, can an AI understand its own code? And to answer those questions, we have done some recent and very novel research, I like to say, Markus.
Yeah, I'd like to say the same. We submitted this for peer review last week, so this is really, really fresh. And this time we looked at code from the domain of competitive programming. Has anyone here done any competitive programming? Not so many, but it's a niche, of course. It's a special thing going on. You might remember AlphaCode made the headlines a few years ago, published in Science. That never happens for computer science research typically, so this was a big thing. DeepMind trained this AI to perform well at competitive programming tasks. And the training data they used is public, so we now sampled code from this training data, 5,000 Python files in this study, and some of the files look horrible. I don't know if you have seen any code from this domain, but I mean, it's all about speed and functionality. I mean, functional correctness as fast as possible. This is what the competition is about. So, what is also important here, we had the solutions then, and the corresponding test cases. So the test cases are very important here because the organizers of the events, they carefully design the test cases to make sure they can see if a solution actually works. So we trust them. But the code looks horrible, so we tasked various LLMs with refactoring. So we asked LLMs to simply improve maintainability. And as you might understand, it didn't always work. Sometimes the functionality, semantic behavior wasn't preserved, right? So we count those incidents, we count the break rate simply. I mean, did the test cases still pass after having made the refactoring? And here comes the cool new results then. We did this study for a handful of open weight models from the big providers. And also we tried Sonnet 4.5, the latest September release from Anthropic, to also cover state of the art. And what you will see here is code health on the x-axis. So higher code health is to the right. And then we have the break rates on the y-axis. And we want to have that low, right? And what you will see now when I animate this little graph is that across the different large language models, we have this consistent trend that the break rates go down with higher code health, right? So this is an interesting and very important finding going forward, we believe. And it deserves its own takeaway message. So from this section, I really wanted you to take this home, that AI expands our code's audience. There is a new stakeholder in understanding the code, right? So code needs to be understandable for humans and machines alike. Yes, but how can we then ensure this, Adam?
Yeah, what tools and techniques can we use now for safeguarding our code? I think we all agree that there has to be some kind of safeguarding, but how does it look in practice? How can we ensure that the code remains understandable for this dual audience? What would you propose, Markus, as a first step?
As the first step, there are many things we should do. A little bit of training, I think, would be good, actually. But when it comes to tooling, which is the focus of this talk, you remember the horrible C++ we saw in the beginning, right? So we want to make sure this does not enter our code bases, right? And a very good place to start, we believe, is the IDE. So we have developed this IDE extension with a code health monitor, which means whenever an AI then would propose some change that introduces a new code smell, it would immediately flag this. Then you can see that the code health, if you accept this change, would actually go down. So you can stop this before it gets committed to the code base. So this is quite early. And Adam, first man on Earth, you're good at early things, right? Can you beat the earliness of this attempt?
I do feel the pressure, so I have to make an attempt, right?
Yeah, you have to.
Yeah. So to me, one of the big game changers of the past year is MCP. And you have probably all heard a lot about MCP already in the conference, right? But what I like about MCP is that, it can having an MCP server that can deliver code health insights to the AI allows us to get even earlier feedback than what we can get in the IDE. So I want to show you an example on how that looks. So I'm back here to my example with generating amplitude events, but I now instruct the AI to pay attention to code health, right? And when I kick off the AI, it's going to invoke the MCP server. You see how it calls for a code health review. It gets the deterministic results back. And this is really important because this is deterministic information that gets into the AI. And what I see happening now is that based on these code health insights, the AI can discover the code quality issues on its own and can quite often even propose a plan to remediate it. And it's very easy to see how a fully agentic solution can easily go back and just iterate on the code itself. So MCP is definitely a true safeguard that I would like to have. I would like to have instructions like that in my system prompt or global instructions when I code with AI. Another big advantage with MCPs that I've started to explore recently is that MCP allows us to refocus AI on the real bottleneck in programming, which is human comprehension. So now I want to show you a different piece of code. This is really just a small snippet. This is one of my favorite pieces of code. I use it all the time for demonstrations and performance tests because this is gc.cpp. This is 40,000 lines of C++ code. This is the .NET garbage collector. So this is the code a lot of you have running on your laptops. Now, what's interesting is that how long would it take you to review and understand 40,000 lines of code? I'm not sure if it's even doable, right? But a couple of months at best. And how long would it take you to form a plan to remediate all the accidental complexity and technical debt there? I mean, we're talking about years here. But what's so fascinating is that an LLM is really good at summarizing large amounts of complex information in an accessible way. So with an MCP server, I can simply ask my Copilot or my LLM to review and summarize the code quality issues in this complicated hotspot. And it will do that. And even better, the AI will even let me define a plan. It will help me build a plan on how I remediate that technical debt. And it will be a plan that takes risk into account. So I start with some low-hanging fruits, things that are simple to change, but kind of set the foundation for deeper and more impactful refactorings later. So to me, this is the area where there's most promise in AI-assisted coding right now. to help us understand existing code and make it simpler. So I do think that on AI, together with the right MCP servers, might be the ultimate UX for working with legacy code. And while an MCP server helps with safeguarding at the code level, I also think we need to consider the macro level, the system as a whole, the whole code base. And by leaning on the research that Markus presented, we know, or we can know upfront where the AI can do a good job as well as where it's going to struggle and hallucinate. And what kind of surprised me when we start to look at these initial research findings is that there's such a narrow window for AI correctness, right? The moment we step outside the boundaries of healthy code, the hallucination rate goes up dramatically, 30%. And in that study, we were only able to measure down to a code health of 7, right? So that's really just the higher end of the scale. The actual code health metric goes all the way down to 1. And we see from other research that we have doing that the relationship is usually non-linear. So at this point, we don't really know what happens when you have a really, really poor code health. How well does AI do? But it's very likely that it's non-linear. The hallucination rate will increase quite rapidly. So if we have this knowledge and we want to reap the benefits of AI-assisted coding, we can use this to minimize risk. Because if we know the code health of every single piece of code we have, of every single package, every single service we have, we can use this to determine AI readiness. So even inside the same code base, I have seen that quite often parts of the code are in a fairly good shape. So these are parts of the code where I can safely, or at least with limited risk, adopt AI and benefits from its acceleration. Whereas other parts of the code might be too dangerous. The hallucination rate is likely to be too high to be useful. So here I would avoid using AI. And if I try to sum up everything we have talked about, it is simply that to really succeed with AI, I think number one step is to set realistic expectations. Because as we have discussed, typing never was the bottleneck in programming, right? And I also think it's really important to make code quality a KPI, because the code quality is going to be something you want to enforce for humans and machines alike. You want to make sure that whatever the AI generates, it's healthy code, right? And also think going forward, since we will see more code than ever before, it's really important to optimize and recognize the increased importance of understanding code over merely writing it. And this is where I think that ironically AI can add the largest value, in particular when combined with a deterministic MCP server. And finally, aim for AI-friendly code. And you remember the last slide, right, with the AI readiness. What this simply means is that you might have to refactor code in order to be able to benefit from AI with acceptable risk. So right now, we're at this stage where we can either thrive or collapse in the age of AI. And I hope that we managed to give you some guidance on how we can design code for humans and machines alike, and how we can benefit from AI without taking on unnecessary risks. And we wanted to leave you with a couple of references. If you want to read up on more on this, if you want to take a look at the MCP server we built, or you want to read up on the code red studies to see the correlations between code quality and business. And we have a couple of other things as well, Markus, that might be worth pointing out. And of course, if you're interested in all the references that we had throughout the slide deck, then please grab it via the QR code. And the reason this was possible was largely thanks to CodeScene research. So if you find value in this, please consider to take a look at CodeScene. Please consider to support us. Yep. And we'd be happy to take questions, right?
Absolutely. Absolutely. We have some time.
So first of all, thank you so much for listening to us. Thank you very much.
Thank you.
And 5 minutes for questions.
Yes, there is one in the corner. You get to go first. Is there a mic, or should we just scream?
So you told us about the code quality metric and how it's a good way to check if code is ready for AI or not. Have you tried having a mechanism that basically blocks AI from touching code that isn't AI ready?
Wow.
New feature, right? Yes.
I didn't think about that before. I like that. So, you want to repeat it, Markus?
I can repeat the question. So we have this metric, code health, right? And it seems to correlate with AI readiness, at least according to our most recent study. So the question was if we had like an idea of developing a feature that kind of could stop AI from, touching code that is not ready and has poor code health. So that's how I interpreted the question, at least. Yes, good.
Yeah. And I just commented that we don't, but I think it's a very interesting use case.
Should we go here? Yes.
To what extent could I prompt my way out of this? So take code health principles and put them into the system prompt, or have another agent that plays code health's role?
So I'll repeat the question and you can try to answer it. So to what extent can we prompt our way out of this? So adding information about code smells we don't want to have to the prompt, I guess, up front, rather than waiting for the result and checking if they're... Or having a code review agent.
Yeah, I think we're touching upon the solution. So this is basically what we did with the MCP. So the MCP server that we showed you, it gives you a code health review. So it will tell you not only is the code good or bad, but it will also tell you exactly about what code health features were included, which code smells. So it might be that it says that, hey, this function here that you're about to change or generate or whatever, it's slow on cohesion, it has deep nested logic, it suffers from primitive obsession, right? And all of that is going to enrich the context for the AI and will help it do a better job. We see quite a dramatic impact there. And then, of course, the AI can kick back to the MCP server again and verify its output and make sure that it's healthy. So that's what I think is important, that we get a ground truth and we get an objective way of assessing if one piece of code is better than another.
And I can answer the first part of the question partly also because we have another paper we also submitted last week actually to another conference where we looked at prompt engineering and maintainability, refactoring operations. And there was a significant effect when we had more advanced prompting. We had only zero-shot prompts actually in what I showed here before, but if we have more advanced prompting techniques, we can make it better. The LLMs will act when they get more context, right, of information, what code smells to remove, etc. 10 percentage points was the average increase, but at the cost of a lot of more tokens. I think it was an 80% increased cost in tokens to get this increase in effectiveness of the refactoring operations.
Did we manage to answer the question?
In various ways. Yeah, we had a question here as well. Yes.
So do you find that the programming language influences the quality of the code generated by the AI or the vulnerability of the AI to bad code?
So the question is, to what extent programming language influences the quality of what the AI produces and the risk of using AI agents? And this is a common question, right? I can start with this paper we read up. I saw some paper from a Greek research group recently where they looked at internal perplexity metrics in the LLMs, how confused the large language models are when they are processing various code snippets from various languages. And there is systematic differences between languages. We haven't studied the differences yet. That's our plan next step. But the Greek group showed that statically typed languages are easier to deal with. Java was quite okay, C#. The worst ones, Perl was there. And actually, JavaScript was also a bit down, but Perl was the worst, I remember. But they also don't have so much training data for Perl, I guess. But there are differences, yes. C++ is not easy. That I should also mention.
Yeah, that was maybe the surprising finding, because it's a statically typed language, right? But the LLMs do really, really poorly on C++. And probably it is due to the diversity of what we call C++. It's not really one language. It's like 5 different things under one umbrella.
Yeah,
so
it's a tricky one.
But it's interesting. I also think it explains one of the observations we do all the time, because I'm really fortunate to be able to meet people from all over the world working in different organizations, part of my job. And very often I hear so conflicting views. Some people claim that AI, it's absolutely wonderful. It speeds up things a lot. Whereas others are more like, yeah, we tried it, didn't work at all. And it kind of always confused me, this this contrast. And I think that this is part of the question, that the technical context is completely different. They probably work in different technologies, and most likely they have very different code quality, right? So context is, I think, a large predictor of AI performance.
Yep, but we will hang around in the speaker's corner. Time is up for us.
Yeah.
So thank you very much. Good questions, and good combine.